Welcome to Advanced Embedded Systems. We are in lecture 19 where we are going to create a soft core with our MicroBlaze and connect that to a custom intellectual property core of our own design. So again, do your time logs, MicroBlaze, and we're going to add a custom IP core. How we're going to do that. So we're going to, on our Arctic 7 design, which we've already learned how to do this, create a block design where we're connecting a MicroBlaze to an AXI bus to the UART light, and then out to the real world through the XDC constraints file. But then on that bus as well, AXI bus, similar to a PCI bus, just smaller, we're going to connect our Lecture 19 counter. And we're going to connect that via a couple modules when we create our peripheral core called MyCounterIP, the top level, and then the connection to the AXI bus. So the top level will connect to that bus, this AXI light, and then we're going to connect our counter inputs and outputs to different slave registers. And there are going to be 32 slave registers, 32 bits wide, we're able to use, and we're going to connect those control signal and then D and Q signal to slave register 0 and slave register 1 respectively. We're also going to swizzle off 8 bits and connect them to the LEDs so we can see our count on the LEDs. And then we're going to connect that through another XDC file to those pins on our FPGA. After this lesson, after we develop this design, you're going to continue the development and add in a roll signal in the homework where you're going to connect that roll signal to slave register 0 in anticipation for what we're going to learn about on our next lesson, which is to connect that roll signal to an interrupt. Next lesson in lecture 20, we're actually going to utilize the interrupts and that roll signal. So you might think about this already, since that roll signal is only held high when the count is to max count, which is FF. For our counter, you might have to tie it, since it's only held for one clock cycle while it rolls over, you might connect that to a flag register, just similar to what we've learned about already. So set or process Q and not the clear bit. So next lecture we're actually going to connect an interrupt service routine to execute when we reach max count. And then we'll have another slave register in our AXI light where we can tie to a clear signal. Notice for our counter we have D, the load value, and the Q value loaded on the same register, but for the set, it uses a roll signal, and then that output of that flag register will go to the slave register 2, and then we're going to set a clear value from slave register 3. So we're going to learn how to read and write through the process of today's lecture to those slave registers in our IP core. All right, so workflow has 3 main steps. First, we start with what we learned in the last lecture, which is MicroBlaze plus a UART light in the IP integrator. I'm going to show you that whole first step just to remind you of the process. But if you want, you can skip through this video. If you already have it created, skip to the next part, which is to create the package and the custom IP core. So let's start with the design. So starting with the tutorial. Again, general design flow, creating your new project. All we're going to do is we're going to start at the beginning, create a new project. We're going to call it something like lecture 19. RTL project, not going to add files or constraints. We're going to connect to our board if you have your board's port connected, and then finish that. That follows right along with the steps in the project creation. Now we're going to create a new block design. So create a block design, call it design 1. Then we're going to add an IP. Click here, click there, it doesn't matter. Add IP, we're going to add a MicroBlaze. Click on that. One block automation. Local memory 32K, cache 16K. Our controller, just like tutorial. Click OK. Once we do that, we're not going to run connection automation yet. Then we run clock wizard 1. We set it to the system clock. Set up a new output of 200 megahertz. 200 megahertz. Put low input. Changes our block diagram. Click OK. Just like this. Now we add our, still don't run connection automation. And add our UART light. AXI UART light. Connect that. Alright. Now, this one we run connection automation for the first time. Notice these two AXI, DC, and IC signals are in this list. They don't show up in here. You do not select them. Later on it shows you not to select those and make those connections at this point in time. If you do, this is going to cause you huge errors with your AXI port. So we're going to connect everything else automatically. You can see what they're going to get connected to, but by clicking on them, click OK. DC and IC are still not connected, which is good. All right, now like that. This says to manually connect the reset pin, which it's already set. Now we're going to add in the mix 7 memory interface generator. Add that in. Block automation, DDR3 SD-RAM. We'll generate that just like this tells us. Block automation connected to DDR3. You're going to get this error, which is okay. Click OK. Run connection automation again. And again, do not connect AXI, DC, or IC buses. Run connection automation again. And as you do this, you can also refresh as you're going along. Now, next step is we do, oh, and I screwed it up. So the manual connection, what you can do, if you screw up and you connect the wrong clock to this, notice we have the 100 megahertz clock. I can actually delete this and run a connection automation. Select call, let's set it mid 7. I want to make sure it's connecting to 200 megahertz. So we do that and reconnect it, and now that system clock is connected to 200 megahertz versus the 100 megahertz. All right. Now the next thing we do is click here. You can regenerate the layout anytime you want. And click here on DDR3. And make that external. I was only supposed to do 1. I made 2. I'll just delete that one. Should be able to click there and put it in the external. You want to click on that one connection and make that one connection external. Alright. Regenerate. Now we can validate our design. Validate our design. Things should look fine. Alright. This is where you would normally create an HDL wrapper. Then you would generate your bit stream and make sure it works, but we're going to skip that step and move right on to the next step in our process, which is create and package your new custom IP, your hardware, and import that into our design. So, we're going to import it into our lecture 19. We're going to add that in. So we already have our MicroBlaze and AXI UART light set up for us, which we already did. Now we're going to create and package our new IP and import it into our design. You can follow this tutorial online, otherwise follow the video and I will show you what to do. So open Vivado and create a new project, which we already did, and we're going to create and package new IP under tools. So under tools, create and package new IP, click next, and then we're going to do AXI4 peripheral, next. I'm going to name it counter, my_counter. I'll call it version 2 because I already have a counter. And I'll make this one version 2. You can create yours and make it version 1. My new AXI counter. And next. Steps, input the name. We're going to use 32 registers. That's the number of slave registers we want to be able to communicate with. Right now, you could do less, but right now we'll just use 32 because that's what the example I have for you. And that's what the example code I have online if you wanted to look at that. Alright, next, edit IP. And click next, and finish. And it's going to open up a new Xilinx window where you're going to be editing your IP core. Drag that over. So you have edit my counter version 2 IP, and it put that into basically IP repo folder in my IP repo. I left it and in the self-defined location, so it's on the same level as your lecture 19 folder. It's in a folder called IP repo, and it's going to create a my counter version 2 IP folder in there, and that's where I'm going to look in the repositories to find these. So make sure you put that there. All right. So as you look at this, it created some of some files, some wrapper files for you. The top level VHD, which we're going to update, and then the AXI level connections. Both of these files we are going to update as we move along. If you go online to the website, I have examples of the user logic and the top level interface. Both of those are here. You can take a look at them. We're going to walk through how to update these with the proper values. You could potentially copy all this, although it's going to be renamed. Copying and pasting it all is not a good idea. I want you to understand how to put all this stuff in there, so we're going to walk through how to do that. And what we're going to try to do is this user logic. We're going to drop in lecture 19, which that you can utilize. Lecture 19 VHD. That file is just a basic counter where you have hold, count, up, load, and sync. All that is redefined. We did that in lecture 11. It's the same type of code. Alright. But we're going to update the user logic to instantiate that and make the connections to the bus, the slave registers, and everything to make it connect with the outside world. Plus, adding in these LEDs up in the hole, in user logic, and in the top level to be able to make it connection to the pins on the chip. Alright? So, again, your design will look a little bit different. It won't have the lecture 11 behavior, the counter actually connected just yet, but that's what we're going to learn how to do. So, how do we do it? How do we add the lecture 11 counter? All we do is we add the lecture 19 VHDL file. You can do this several ways. You can download it and then import that design into your project, or you can create a new one and just copy it in. I'm going to go ahead and add that source, just like we would in a regular program. Add design source. I already downloaded it, so add files. Downloaded code for lecture 19 VHDL, and I'm going to copy it into that directory. Copies it in. It's not connected, so we still don't have it connected to the user logic here, so we're going to have to walk through how to do that. So, notice with your handouts in front of you, like this. The truth table for your counter is in the comments. 0, 0 to hold, 0, 1 to increment, 1, 0 to load, 1, 1 to reset, and so on and so forth. I have some values that you can start inserting in there. Right now we set this up as a generic, and so in lecture 19 VHDL, what other libraries must be loaded? If you look at this handout, what libraries do we need? Obviously, we need the IEEE logic, just like you would normally see in the file. IEEE standard, standard logic, and the numeric standard, right? Because we're counting up, right? Do we use the work lecture 19 parts at all? No, right now we're not, just because I was not able to get Bravado to recognize those parts folders for IP cores. Okay. Again, so let's look at this. You have this on your handout. This is set up as a generic, so a process queue needs to have filled in with n-1 down to 0. And then based on these values, this one should set them all to 0. This one should be process queue plus 1. 1, 0 should be load, so basically taking our D value and putting it in. And then the last one will be reset again. So others equal to 1 for reset, otherwise unsigned, typecasting the D input, and then process Q plus 1. And we've already looked at this and understand how that works. Some hardware notes to the counter. So the user logic, what do the generics num, reg, and slave width do? So let's take a look at this. So we have this. It's also on your handout. If you look at that, slightly down. So in your user logic, what do the generic does the generic AXI data width do? And if you look in your code, up at the top, you have the generics. You don't have the number of registers anymore, but if you did, it would be 32 bits, 32 registers. Each of them are 32 bits wide. So notice down below when it's setting up your slave registers, it's that width minus 1 down to 0 when you set up those values. So address width is going to be 7 bits. In that user logic, what are the two roles that slave register 0 is serving? There's basically, if you look at slave register 0 in your code, right, here is the signal. There is one part of it that is going to be on the clock. We're assigning slave register 0 to a value. So we're writing the values here to slave register 0, and we're reading those values in the read section at the bottom. So we're address decoding for the reading of the register. Slave register is being read and putting on the data line out. When you look at the code, the block diagram that we have, we're going to be reading from Q, but writing via slave register 0 to D. Okay? And you can see that in the sample code that I gave you. Slave register 0. Writing slave register 0, bit 7 down to 0, to D value, and then we're taking standard logic of Q, and towards the bottom part where we're reading registers, we're assigning Q standard logic plus a bunch of zeros in front of it to get it 32 bits to go to that register data out, where slave register 0 used to be writing to that address, slave register 0's address on those read lines for decoding what does slave register 1 serve in your design? Slave register 1 is going to be holding your control signal, so we're going to write the control signal to that. And you can see that in the design right here. Slave register 1, bits 1 down to 0, so those 2 bits are control signals in the user logic. So when slave register 0 is on the left side and the right hand side of an assignment, I showed you those already, right? It's on the right hand side here when it would have written to the bus. So that would have been a read side. And then left hand side is here, right? On the right. Okay. On line 62 of our handout, so again, next on line 62. That should actually be on line 73. What is the 00? The 6 zeros served in the front on the handout. Basically, it's setting the upper bits to 0. So we have 31 down to 8, which is 24 bits. 24 bits is 6 nipples, or hex digits, setting them to 0. Okay. So, let's start hooking this up. So again, when you look in your user logic, we're going to start plugging in some of those values. Notice on these add user ports, I have a user and LED port here. We're going to start adding those. We're going to add in the signals for the components. All of this is in the handout. It's also in the examples that we have. So, all these signals, we're going to start adding those in and then filling in the values for the user logic, which we already know anyway. All right, modifying the counter. First thing we need to do, so we'll take and we'll add in numeric standard all for that. Since our counter uses numeric standard, we're going to have to add at the top, add the library for numeric standard all, which it's already got it, so we don't even have to add it. Next step would be adding in our component. So we're going to add those user ports, which you can copy it from the lecture slides or from the handout. We're going to add in that line for the LEDs. So under user ports, not under generics, we're going to add in the LEDs. We're going to do a port map to get that out of our user logic. So you have this original design. So in order to get these LEDs to port map them out, we need to extend those LEDs out via the port map. So on the port map for the entity, add the LEDs, and then on, it shows that, where it's located, and we're going to add the counter component declaration in there as well. And it'll be where you're adding signals. We're also going to add a signal for our Q signal, but we're going to create a generic component declaration in our signals. Now past it. Signals for user logic, add in here. Kind of make it a nice note for you. So we're going to have the signals. We're declaring our lecture 11 component with its input and output values and port map, and then we're creating a signal for Q, it's Y. So we drop that in. This is what it looks like when it's done. You can fill in those values on your handout as we go. Now we're going to connect our counter implementation Q signal to the output slave register 0 by adding those zeros and the 24 zeros in the front end to connect it to the right bus, plus type casting our standard logic vector of Q. Right. So we connect that to the bus. So we scroll down to we see those right values where slave register 0 is written to the output. For reading, we're just going to put in zeros and the standard logic vector. It's going to come up with an error right now because we haven't assigned that value yet. So, if you want something to go outside of the chip, it has to be in the T description. First, it has to be in the counter.vhd, and then in the user logic counter, mycounter IP underscore S00 underscore AXI VHD, and then eventually to the top level to get to the system.xdc file. So eventually that system.xdc, maybe lecture 19.xdc, we need to add those LED pins to that constraints file. If you want it to go to the MicroBlaze, then that's actually deprecated for the first one. But we're just basically going to connect them to the read select and the slave bus. So we're going to connect it to those slave registers on the bus. Otherwise, you have to port map it out to that lecture 9 LED XDC for those LEDs. If you want it to connect to the MicroBlaze, we're going to connect to the slave register via the AXI bus. All right, so continuing on. I did not add in the last user logic. So after we created our component declaration in the signals, let's get at this one, where we actually add the user logic, which is adding this counter code, and so that is the instantiation, declaring it as an 8-bit counter. We're going to connect our, it's all the way down at the bottom, add our user logic here, and add instantiate it as an 8-bit clock, connect it to the AXI clock, AXI reset, the control, we're writing bits 1 down to 0 for the slave register 1, just like the diagram shows. And slave register 1 is control. And then slave register 0, set down to 8. We're going to cast unsigned and set that into a B value. So we're just going to strip off slave register 0 signal that already exists. And Q is going to go out to the LEDs, but it's also going out to our standard logic vector. Now to make sure some of the squares there. Okay. Now we can go back to the top level design, so that would be the my counter IP. And then we're going to port map out our LEDs through that. So we're going to have to add it to the declaration and instantiation within that top level design. So we have our alright, so now we need to port map the LEDs in the entity and the architecture in our top level to make sure that goes out to our block top level design of our system. So first we're going to add the port here in the entity. So we'll add user ports here. Add our entity. It's a lot easier to add it at the top of the entity than at the bottom. So we add the LED for 8 bits. And then we need to add it in architecture as well. In architecture, under the component declaration, we're going to add the LEDs there as well. Copy that, and here in the top of the port map, we'll put it in the same location, always at the top, it's easier. Add it to the architecture component declaration for that user logic. And then the instantiation, we need to tie the LED signals together in the port map as well. So we're going to tie LED to LED, and we'll make sure we match the port mapping. LEDs, tie the LED with a comma after it, and tie that to basically port map those LEDs all the way out of the user logic. When you do your homework, you're going to actually add a signal called roll, and you're going to add that signal all the way out as well. Port map it all the way out to be able to use that as an interrupt. But before you output it, we're probably going to tie that to a flip register. So, port map that out. Alright, so, again, at the top, we have numeric standard added. I follow the slides. Numeric standards are already in there. I added the ports, the LEDs. And then I added it in the component declaration of the user logic portion, instantiation, or declaration. And then I added it in the instantiation, LED tied to LED signals, same as the other, the top of that AXI, user logic. And then we need to package the IV core. When we're doing this, you're going to be selecting a few things. Select on compatibility, Arctic 7. You're going to, as you go along, you're going to merge the changes from the customization parameters wizard. And we're going to process through each of those values to get down to the GUI. And the GUI should show the LEDs coming out, and then the AXI connections on the left. And I'm going to show you how that does. So identification, compatibility, Arctic 7, file group, one merge file groups, customization, merge source changes, ports, we have the LEDs going out, and IXI coming in. Everything looks good, and then we repackage IP, and yes, we want to close the project. Just like this, repackage, and yes, we want to close the project. Now, you can add that to your lecture 19. So go back into our design, lecture 19, and I can add, type in counter, and I see my counter version 2. Add that file in there. So lecture 11 counter IP core, lecture 19 is there, and we added it. We have our LEDs outputting. We can run our connection automation automatically, and it will show us it's hooking up to the 100 megahertz clock, and then the AXI bus connections. And then, once we do that, then we want to make our LEDs external, so put the pencil on that, and make it external, but notice the names it LED _0, you can actually just change that to LED and try to make it easier for later. Because otherwise you have to change your constraints file to match the signal name we're using. Right, so I changed that to LED instead of LED _0. Now we need to add these constraints. And so I would actually go in and copy those values. LEDs from the slides, right out of the slides, and then I'm going to go in here to my design, F1 design, and add a new source, add a new create constraints file, and create a file, and just call it lecture 19.xdc. Done. Finished. And just open that up and I'll drop in those properties. And notice LED is not LED _0, so make sure that matches what's in the diagram for those pins to be able to make that connection in our diagram. Thus, for lecture 19 XDC on the right, we notice those pins are connected via the bus, via these via this XDC file. So let's save that. So that net LED is connected to those pins and output pins. Right? Okay, so now we created our design, dropped it in. If we wanted to go back in, we could actually right-click on it and edit an IP packager if you wanted to modify it. So when you're doing the homework, you can actually modify it to add your roll signal in. You edit an IP packager, and then it'll open up a new project name, and you'll be able to go in and then re-edit all the files, and then repackage. Make sure you repackage the IP after you're done. So you're going to have some errors. You're going to merge all the changes and then repackage your IP. And then once you're back into your main design, You can actually refresh your IP catalog because it'll be out of date. So you'll refresh it and upgrade the selected device. If you had other pins, then it'll add those other ports. That roll port that comes out or something like that. And then you can also verify the addressing for your components before continuing as well. You go under the address editor, you can verify the addresses of your design. Right, so your UART is going to be at 40,600,000. Your IP counter is at 44,800,000. And you can, once that's all done, let's verify that here, address editor, you can verify that's the same addresses. You're not even going to change anything at this time. 46,000 for the MicroBlaze, and UART light. UART light is 46,000. This is at 0, and then 44,800,000 for the counter. Alright, then you can click Validate Design. So go back in here. Validate Design, should be all good. Now I have to regenerate the wrapper. Like it says, regenerate the design and wrapper, and then regenerate the bit screen. Right. And now you should go ahead and generate that stream and take a copy break. Okay. And now we take a coffee break. And I'm going to do time lapse video to wait for the end of the video. Hope you enjoyed that coffee break. Once the design is completed, then you need to export your hardware and make sure you include the bit stream. So, design generated, and we're going to export hardware, include the bit stream, and then launch the SDK in the local space, just like suggested slides. Launch SDK, and then we're going to start a Lecture 19 project on the software development kit. Let's go up. Notes we just got the hardware platform. You can take a look at the system.htf file on the light. 40,600,000, 44,800,000 for your counter. All that is in the design. Now we can go file, create new application project. We'll just call it Lecture 19. Slides. I just opt for a shorter name. Lecture 19, that creates one sport package, and I'll create a whole world. But you can create a new source file, call it main.c, and also it'll already create one for you, so you can just go into your sources. Rename this whole world. Rename. I'll call it Lecture 19.c. Go to the files online. C files. paste it, save it, make sure I'm going to go build. Set up, Terra term, disconnect, connect the new one, Terra term will connect on 9600, and then I can actually run as hardware GDD, go up to the run configuration. The application will have the standard I/O port is going to have it there. Just run it. And notice I give a moment to let you print out, which is what is in the code. If I hit the question mark, I'm going to show you the menu. And there's some questions we can talk about. Slides. So, when you take a look at the code, we have some includes on that file. I have a counter register, which A44A 100,000 I have, that's the base address for the counter Q register. So register 0 is going to be at that register. We're going to be using 8 leasing bits of that to read or write to D, read Q or write to D on that register. Counter control is at the 2 leasing bits for register 1, so at 4, since it includes the registers, the address, and then the roll later will be also register 2. I'll be able to set up for trying to find some counts, counter controls. And then the UART is like a 440,600,000. And create function prototypes for the permissions as you need. Inside, it's just going to be a reading value of the UART. Question mark will output the help menu. We can do a loop back. Basic value on loop back, so it's just going to print our values whenever we type in, it's going to print back out. Whenever I count up, I send out the count, and then hold, and it's going to roughly count out by 26 or 27 depending on our system. Also set start, and that'll implement the counter, and it'll just go really fast because the clock is so fast. That's where this one 2-7 hex counts before we can actually hold it. That's sending out those 2 commands to the counter. Stop the counter with the big S, and L, we can load value in, take a look at that, and then reset the counter with the counter. And then F will flush the counter. And then anything else will stay its own. And that is our main program. So, let's take a look at some of these values before we go to some of the questions. So, here's our help menu as we look at it. When I hit the C, all right, so some of your questions, the C command Why doesn't it count up by 1? Notice it takes a while for the software to actually send out these two commands to count up and to hold. So with a 100 megahertz clock for our software, it takes almost 27 clock cycles or counts for it to start and stop. So to be able, from once it starts, to be able to send that signal again through the slave registers and read it on the hardware. Hardware is extremely fast. On line 130, why did I subtract 30? If you think about it, it's an ASCII character, or a value between 0 and 9, and stored in the counter. Right, subtract 30. I'm only using 1 byte at this time. After loading the counter on 132, what should be done is missing 132. We're loading. But what's missing out of that is we don't set it back to the whole signal. Right? We're just setting the load signal. So you might think about that. What line of the VHDL code in the EXI is activated when line 80 executes? 80 executes, reading the Q, what line? When we're reading that count Xilinx in, count Q register. Think back to your handout. Activated in here is this line right here, line 73. That's where it's taking that standard logic. Value of Q and pending zeros, putting it on that bus. That's when we're reading that value. What line is then activated when 141 executes? It's 141. Someone's out, setting it to the counter reset. That will be this line here, line 85, counter reset. We're writing to slave register 1, those control values, and that's writing to that generic control value. VHDL, that's your control line. That will be executing this line, and we're doing a synchronous reset. Okay. What appears to be the naming convention of the hardware registers. Entity level followed by the signal name and then the register. So basically count Q underscore register, control underscore array. That's kind of the way I name these registers that you're reading for your slave registers. All right, and that concludes this briefing. Good luck.